The universe is vast. From the tiniest particles to the largest galaxies, the cosmos challenges our comprehension. To truly grasp the grandeur of the universe, we need to understand its scales. We need to compare, to contrast, to journey from the infinitesimal to the immense. We'll traverse the universe from the very essence of matter to the celestial bodies that grace our night sky. Prepare to be amazed by the sheer range of sizes present in our universe. It's a quest to understand our place in the grand tapestry of the cosmos. Imagine a camera with infinite zoom. We begin our journey with this camera focusing on the smallest constituents of matter. These are the building blocks of everything we see and touch. We'll zoom out, gradually revealing larger and larger structures. From the heart of an atom to the complex molecules of life, we'll witness the elegance of nature's design. Each level of this cosmic zoom will unveil new wonders. We'll encounter forces that govern the universe at its most fundamental levels. A grapefruit representing the Earth, a grain of sand standing in for the moon. Such comparisons will illuminate the vastness of our universe. Our journey will take us from the minuscule realm of quarks to the colossal presence of planets. We'll explore the incredible density of neutron stars and the mind-boggling emptiness of interstellar space. Prepare to encounter objects trillions of times larger and heavier than our own planet. Each step of the way we'll compare and contrast. By the time we reach the end, you'll have a newfound appreciation for the scale and majesty of our universe. Our exploration into the universe of scales is about to begin. Our journey begins in the quantum realm, a world governed by laws that seem strange and counterintuitive to our everyday experience. Here we encounter the quarks, fundamental particles so small they exist on the very edge of our understanding. Quarks come in various flavors, each with unique properties and characteristics. Up quarks, down quarks, charm quarks. The names themselves hint at the exotic nature of these particles. Quarks are never found in isolation. The strong force is what binds quarks together to form the protons and neutrons that reside at the heart of every atom. Moving up in scale, we encounter another fundamental particle, the electron. Electrons are much smaller than protons and neutrons, yet they play an equally crucial role in the structure of matter. While quarks are confined within the nucleus, electrons exist in a cloud surrounding it, constantly in motion. Their negative charge balances the positive charge of the protons, ensuring the atom remains electrically neutral. Electricity, magnetism, chemical bonding, all are governed by the behavior of these tiny particles. Comparing the size of a quark to an electron is like comparing the size of a grain of sand to a mountain. To put things into perspective, if an electron were the size of a basketball, a quark would be smaller than a single atom within that basketball. The difference in mass is equally staggering. While electrons have a tiny mass, quarks are even lighter. The majority of the mass of a proton or neutron doesn't come from the quarks themselves, but from the energy binding them together. Understanding the relationship between quarks and electrons is crucial for comprehending the building blocks of matter. Having explored the realm of quarks and electrons, we now journey deeper into the heart of the atom, into the nucleus. Here we encounter the particles responsible for the atom's mass and identity, neutrons and protons. Imagine a bustling metropolis at the center of a vast, mostly empty city. That's the nucleus, a tiny, dense region packed with protons and neutrons. Protons, with their positive charge, are like the city's power source, providing the electrical force that holds the negatively charged electrons in orbit. Neutrons, on the other hand, are electrically neutral, like the city's infrastructure, providing stability and structure to the nucleus. Despite their lack of charge, neutrons play a vital role in the stability of the nucleus. Think of them as the peacekeepers, preventing the protons from repelling each other with their like charges. The strong force binds protons and neutrons with almost equal strength, overcoming the electrostatic repulsion between the positively charged protons. The number of neutrons in an atom can vary, even within the same element. These variations, called isotopes, can have significant effects on the atom's properties. Protons, with their positive charge, determine the atom's atomic number, its fundamental identity. The number of protons defines the element to which an atom belongs. The combined number of protons and neutrons determines the atom's mass number, a measure of its mass. This number can vary due to the presence of isotopes, but the atomic number remains constant, defining the element's chemical behavior. From the lightest element, hydrogen, to the heaviest naturally occurring element, uranium, this delicate balance underpins the diversity of matter we observe. By understanding these particles, we gain insights into the creation of elements, the energy production in stars, and the fundamental processes that shape our universe. We have explored the bustling metropolis of protons and neutrons at the heart of the atom, but now let's take a step back and appreciate the sheer dominance of this tiny ruler, the nucleus. If an atom were the size of a football stadium, the nucleus would be like a marble, sitting on the 50-yard line. Yet this seemingly insignificant speck houses over 99.9% of the atom's mass. The density of the nucleus is mind-boggling. This incredible density is a testament to the immense power of the strong force holding the protons and neutrons tightly bound within this tiny volume. The nucleus, despite its size, dictates the atom's identity and governs its interactions with the outside world. Surrounding this dense, positively charged nucleus is a cloud of negatively charged electrons, but rather than orbiting the nucleus like planets around a star, electrons exist in a more abstract realm governed by the laws of quantum mechanics. These electrons occupy specific energy levels or orbitals, forming a cloud-like distribution around the nucleus. Electrons can jump between these energy levels by absorbing or emitting photons of light, but they can't exist in between these levels. The arrangement of electrons in these energy levels determines the atom's chemical properties. Atoms with full outer energy levels are stable and unreactive, while those with incomplete outer levels tend to interact with other atoms, forming bonds to achieve greater stability. From the tiniest hydrogen atom to the behemoth uranium atom, each atom is a universe unto itself. The size of an atom is determined by the average distance between its outermost electron and the nucleus. This distance, in turn, is influenced by the number of protons in the nucleus and the arrangement of electrons in their energy levels. Despite their incredibly small size, atoms are the building blocks of everything we see and touch. They are the bricks and mortar of matter, the fundamental units that combine and recombine to create the incredible diversity of our universe. Atoms, in their quest for stability and balance, join forces to create a dazzling array of larger structures, molecules. Imagine atoms as individual Lego blocks, each with its unique shape and connectors. Just as these blocks can interlock to build complex structures, atoms can link together through chemical bonds, forming molecules. The simplest molecules consist of just two atoms, like the oxygen we breathe, O2, where two oxygen atoms share electrons in a strong stable bond. Other molecules, like water, H2O, are a bit more complex, with two hydrogen atoms bonding to a single oxygen atom. From the sugars that fuel our bodies to the proteins that build our cells, molecules are the architects of our material reality. Molecules, much like the atoms they're composed of, are constantly in motion. This movement, influenced by temperature and pressure, dictates whether matter exists as a solid, liquid, or gas, the three familiar states of matter. Imagine a group of people at a party. In a crowded room, they're packed tightly together, jostling for space. This is like a solid, where molecules are locked in a rigid structure vibrating in place. As the party progresses and people loosen up, they move around more freely, mingling and interacting. This is akin to a liquid, where molecules can flow past each other but remain relatively close together. Finally, as the party winds down and people head home, they spread out, moving independently with ample space between them. This represents a gas where molecules are widely dispersed, zipping around with high energy. As we delve deeper into the realm of molecules, we encounter a breathtaking spectrum of complexity. From simple diatomic molecules like oxygen to behemoth macromolecules like DNA, the range of sizes and structures is truly astounding. Some molecules, like the hydrocarbons found in gasoline, form long chain-like structures with carbon atoms as the backbone and hydrogen atoms branching off. Others, like the intricate proteins that carry out countless functions in our bodies, fold into complex three-dimensional shapes, their form intricately linked to their function. Despite this incredible diversity, all molecules share a common origin. They're all built from the same fundamental building blocks, the atoms, forged in the hearts of stars billions of years ago. This unity in diversity is a recurring theme in our exploration of the universe, a testament to the elegant simplicity underlying the apparent complexity of the natural world. Building with molecules. From quarks to molecules, particles assemble into larger structures. Molecules are the building blocks of our world. Imagine a single grain of sand on a vast beach. Trillions of atoms form that grain. Multiply that by all the beaches on Earth. From rocks to air, water to our bodies, everything is built by molecules. As we shift our focus from the microscopic to the macroscopic, we encounter objects of unimaginable scale: planets, moons, stars, celestial giants that dwarf even the largest structures on Earth. To comprehend these cosmic behemoths, we must expand our perspective once again, stretching our minds to grasp the truly immense. Consider our own planet, Earth. With a diameter of roughly 8,000 miles, it seems like an impossibly large object from our human perspective. Yet, in the grand scheme of the cosmos, Earth is but a tiny speck, dwarfed by the gas giants of our outer solar system. Jupiter, the largest planet in our solar system, could comfortably fit over 1,300 Earths within its volume. Saturn, with its magnificent rings, is nearly as large. These gas giants, composed mainly of hydrogen and helium, are like miniature solar systems themselves, with dozens of moons orbiting their massive forms. And then there are the stars, the true powerhouses of the universe. Our Sun, a relatively average star, is over 100 times wider than Earth and contains over 99% of the mass in our entire solar system. Larger stars, like Betelgeuse and the constellation Orion, are so vast that if placed at the center of our solar system, their surface would extend beyond the orbit of Jupiter. As we explore the universe beyond our solar system, we encounter a staggering diversity of planets, from scorching hot gas giants orbiting perilously close to their stars to icy worlds wandering the interstellar void. Each planet is a unique world, shaped by its formation history, composition, and interactions with its surroundings. Some exoplanets, like those in the TRAPPIST-1 system, are surprisingly similar in size and mass to Earth, raising hopes of finding other habitable worlds. Others, like the hot Jupiters that orbit close to their stars, challenge our understanding of planetary formation, their presence suggesting that planets can migrate over vast distances during their lifetimes. The study of exoplanets is a rapidly evolving field, with new discoveries constantly reshaping our understanding of planetary systems. As we continue to peer deeper into the cosmos, we can expect to find even more bizarre and wondrous worlds, each offering a unique glimpse into the endless possibilities of planetary formation. The sheer diversity of planets we've discovered underscores the dynamic and ever-changing nature of the universe. From the smallest particles to the largest celestial structures, the cosmos is a place of constant motion, evolution, and transformation, a testament to the boundless creativity of the natural world. Our journey from Quark to planet spans a staggering range of scales, from the infinitesimal to the immense. We began in the heart of matter, exploring quarks, those elusive particles forming protons and neutrons. Finally, we lifted our gaze to the cosmos, exploring the immense scales of planets, stars, and galaxies. It's been a journey of perspective, a humbling reminder of our place in the grand tapestry of the universe. The vastness of the universe can be overwhelming, leaving us feeling insignificant, yet this vastness offers a profound sense of wonder, a reminder that there is always more to explore. Every atom in our bodies, every grain of sand, every drop of water, all were once part of a star that lived and died long ago. We are quite literally stardust, connected to the universe. The journey of discovery will never end.